So I want to talk about an interesting circuit that gives us an opportunity to talk about Norton-Thevenin equivalence and how we do these kind of models for one-port circuits. And I want to kind of talk about what potential things I might end up seeing. And I definitely want to talk about where this comes from, but I'll talk about it in a moment. The first question is, you say you get handed a circuit like this, and you go, well, let's look at a possible different cases. And I want to think about what this contrast is. One, imagine that this GS term is just basically turned off, is basically zero. That means there's no current here. That means as if this link didn't exist. So that means I've got a current source, a resistor, and another resistor. And I want to understand, well, what does that effective circuit look like? Well, in that particular case, the easiest solution here, and again, every solution depends a little bit on where you're starting and what you're going to build from. But in this solution, it's going to be, let me do a Thevenin-Norton equivalent of this, which gives me then, I transform this. What this gives me actually a minus 1 volt, right? And times basically just this R, and these two will be in series. Why minus 1 volt? Well, because I have 1 microamp going downwards. That's where the minus sign comes from. And then R1, which is 1 megohm. All right, so this works out fairly well to start with, and you're like, well, if I have a voltage source and 2 resistors, I pretty much have my Norton equivalent. In fact, it'll look like a circuit like this, which is the minus I1 R1, which is the minus 1 volt. And then the 2 resistors are basically sitting in series, which is kind of funny because at first you think these are going to be parallelish, but it's not quite how that ends up working out when you put that part together. And you think, okay, that's cool. Now, if you want to transform this, and so that gives you 2 of the terms, it's 2 megohms. You want to transform this back to a Thevenin equivalent. This will give you a current source and a resistance, but notice the resistance is twice as big, so you expect that when you transform it back, it's going to be half as much. So where this was 1 microamp, this now the effectiveness is minus half a microamp. Okay, not to worry. We can kind of look at that a little bit as we get going. In fact, you could even jump ahead and say, well, imagine now I take this circuit and I put it into a resistive load. You could actually go ahead and solve that because, of course, I know that current source and I know that effective resistance. That resistance of R1 plus R2 is much, much bigger than RL. In the parallel combination, it means it's just going to be RL. So I'm going to have the current of half a microamp going through RL. I could also talk about it as a voltage divider, which would give me an equivalently good approach. But the net result I'm going to get out of that is I'm just minus 20 millivolts. Right? You think about how you sort of say, okay, I'm going to get half a microamp going through 40 kiloohms, which then gives me basically 20 millivolts, and it's minus because of the way that the current is pulling it. Okay, so that works out fairly well. Now the question happens is, well, what happens when I put GS in? And this is one of those questions of, well, what happens when I actually turn on these sources, and what kind of different effects might I see? Now, for those of you who are looking at this from a transistor circuit perspective, think in this case, this could be a current source. This could have been a transistor acting like a current source. This upper structure would be what's typically thought of as a cascode configuration. And in that situation, we know it does a couple things, at least qualitatively. One is that it will simply just have the current go through. Number two is that it typically makes this resistance here look a whole lot larger. The main reason is that this voltage just doesn't move much. When I say that voltage doesn't move much, think about it this way. I can actually look at sort of the loop right around I1 and write equations there. All right. And again, I'm going to look at sort of this, for my effective current, I'm going to talk about, let me measure the current at I1 by just kind of keeping it fixed. I'm going to start off with just writing out the equations and seeing what I see here. And what I realized pretty quickly is that, one, the resistances tend to not be much of an issue here. I get GS plus a 1 over sort of an interesting combination of 1 over R1 and 1 over R2, so that's a parallel combination there. But even at that, the R's are so much larger than what I would be seeing for the GS term that this whole thing basically, I get a very, very simple equation, I1 equal, plus V1 GS equal to 0. V1 turns out to be a value of about 1 minus 1 millivolt. That means that V1 is pretty close to ground, not moving a whole lot. And so this is actually quite an kind of interesting sort of perspective. Whereas if I were to look at it over here, I would argue that like half the voltage comes across that node. So that changes a whole lot of different ways I would think about this. What it turns out as a result is that my effective current that's coming through that, because this is fairly fixed, but then I can then talk about what is V times GS. This is fixed. There's not much going through here because that's going to be sitting near ground when I look at the current. The net effect is that current is approximately 1 microamp. So we'll just go with it being 1 microamp. So then if I ask, well, what is that effective resistance? Well, one of the nice things I can find is that I can just look at the resistance into this node by applying a voltage of V2 and looking at the current that goes to that node. You can think of it as applying a test source and then looking at the current that's going through it. Great. So when I do that, an interesting decomposition happens. That V2 over I can get split into V2 over V1 times V1 over I. Well, why is that at all interesting? Well, if I'm looking at the effective resistance, that's going to basically, I'm going to turn I1 off because I'm looking at the resistance part, not the source part of this. So basically V1 through R1 is just a simple resistor. So this V1I is just R1 because the current that goes in here is the current that goes through R1. There's nowhere else for it to go in that situation. So all I have to do now is figure out what is the V2 to V1. And that just requires, again, sort of a simple equation to write down on this one. What I find is then, and doing some approximation, again, noticing that I've got an interesting R1 and R2 parallel combination there. There is not the sum that's sitting there. It's a parallel combination that you're seeing in there. But even when you're doing that, what you find is, okay, this term is much, much smaller than the GS. And so I'm left with a very simple relationship that I can rewrite as V1 equals to V2 over 1 over GS R2. So sort of noticing some of the key terms that you're going to get in this analysis. Well, taking this structure and then saying, well, what is that going to be for R? Well, I can look at V2 over V1, and that's going to then give, sort of flip things on different sides. It's going to give me a GS R2 in that part, and then the other part here gives me R1. In this particular case, it means that R is about a gigaohm, which is a really, really large resistance now, and that turns out to make it interesting. So that large resistance in parallel with the load resistance is completely negligible, but I've gotten all of the original current. So now this turns out to give me a minus 40 millivolts. But in general, with the main point that you're often doing with such circuits is trying to make something that you get this sort of large resistance. And that's really cool that I can get structures like this, which then allow me to either move that out of the way, allow me to get higher gain, allow me to do various different things I might imagine in different circuit configurations. So this, again, kind of shows you a number of different pieces and parts with what is pretty typical and standard kind of circuit topology that you might want to be able to see.